Next, we're going to show how we can use the frequency response help us analyze systems behavior in the frequency domain. For non-periodic signals going through continuous time LTI systems, we can use that diagram to represent the concept for frequency response. So for any signal, it can be, in the time domain, it can be decomposed into a linear combination of imaginary exponential signals. And this signal going through continuous time LTI system, the output will be modified by the system's frequency response. Using the linearity property, we can understand that the output or the system's zero-state response is the same linear combination. So we can reach that conclusion that the system's zero-state response is equal to the multiplication of the input and the system's frequency response in the frequency domain. So that is the diagram in the frequency domain for the same system. Here's one example. We have a stable continuous time LTI system. It is stable, so the frequency response does exist. And if the input is given there, what is the system's zero-state response? It's quite straightforward that the system's input can be represented in the frequency domain, and the system's frequency response can be evaluated from the differential equation. And the system's zero-state response in the frequency domain can be represented by the multiplication of the input and the system's frequency response. Now we can convert it into the time domain, and this is the system's zero-state response. Here's another example. Again, we have a stable LTI system. And what if the system has two inputs? One is a cosine function, another one is unilateral exponential signal. And what is the system's zero-state response? And we ask you to use Fourier analysis, frequency analysis. So for the first signal, we can convert it to the frequency domain. And the system's zero-state response is equal to the multiplication for the spectrum and the system's frequency response. And here is the system's zero-state response in the frequency domain. But we may have some trouble to convert it into the time domain. For the second input, we can take a look at that signal. That signal does not satisfy the rigged condition, so that the Fourier transform for the input does not exist. We cannot use frequency analysis method to help us figure out the system's zero-state response. There is a relationship between the frequency analysis and the time analysis. We learned that in previous chapter that the relationship between the input, the system, and the system's zero-state response can be described using convolution. Now we learned that in the frequency domain, the relationship can be represented as multiplication in the frequency domain. So they are the same, basically. They just use different basis function to do the analysis, to do the derivation. And we have convolution property to connect these two methods. One in the time domain, convolution. The other is in the frequency domain, multiplication. The significance of the system's frequency response can be described using this statement, that the behavior of the system towards the input actually is modify the input using the system's frequency response. So the frequency response reflects the transfer characteristic of the system to different frequency components. We often call continuous LTI system analog filter because the frequency response can help us selectively allow certain frequency components going through the system, but may attenuate other components or eliminate the components completely. And that is the reason we often call continuous LTI system filters. Here is one example. There is a music signal but ruined by noise. We can hear the effect now. And here is the spectrum. If we know that this is the noise, we can design a band stop system to selectively remove that noise from the signal. And here is the processed music. Clearly, the noise is already removed from the music. The next, we'll try to study for a periodic signal, what is LTI system's zero-state response based on the understanding we learned previously. So this is the imaginary exponential signal. If going through an LTI system, this will be the output. And we know that for periodic signals, we can use Fourier series to represent that signal in the time domain. And now by the linearity of the system, we know that the output will be the same linear combination. So now we understand that the system's zero-state response is related to the input and the system's frequency response. Here's one example. We have a periodic rectangle signal input into this RC circuit, and what is the system's zero-state response? This is the Fourier series for the periodic rectangle signal. From the previous example, we know that for an RC circuit, the frequency response, and we know from the previous slide, the system's zero-state response is given in another Fourier series like this. And we plug both terms into the expression. This is the system's zero-state response. If we set the RC time constant equal to 0.3 or equal to 4 seconds, then the response of the system are quite different. Here is one more example. A music is somehow ruined by noises over there. We can hear the effect. 小城故事多. We can design a system whose frequency response looks like this. And here is the zero-state response of the system towards that input. 小城故事多. Or we can change our design. So for a second system, we can design the frequency response like shown in this plot. And here is the output. 小城故事多. We can try to design a third one with another different frequency response. And this is the effect. clearly they are different. And now in the frequency domain, we can hear the difference and interpret the difference very well. Now, with the frequency response of the three systems, we can interpret the behavior of the three systems quite intuitively. Now, we convert or we analyze the system's behavior in the frequency domain. If we treat the system as a signal transmitter, for example, we have a rectangle signal as the input. Instead of doing this in the time domain, an alternative way is we can convert it into the frequency domain. Similarly, for the system's impulse response, we can also convert it into the frequency response in the frequency domain. And the convolution in the time domain can be converted to the multiplication in the frequency domain. So because multiplication is really easy to understand, so interpretation of the system's behavior can be quite straightforward in the frequency domain. Here is one example. We have an ideal low-pass filter whose frequency response is given here. And if we have three input signals, we want to evaluate the zero-state responses to those inputs. For the second input is again a sampling function. And here is the spectrum in the frequency domain. Multiplication will get the system's zero-state response. And here is the expression. And we can convert it back into the time domain. So this will be the waveform in the time domain. The input and the system's zero-state response. The third input is a periodic rectangle signal. And the fundamental frequency for that periodic signal is equal to 1.25. And for the second harmonic, 2 times omega sub none, it will be 2.5 pi, which is outside the range of the rectangle signal representing the system's amplitude response. So that we understand only the DC component and the fundamental frequency of the input can going through the system. All other components will be eliminated because they are outside the rectangle signal. So that the system's zero-state response will be represented by the Fourier series given in there. And we have only 2 components, DC components and the fundamental frequency components in there. Using the Fourier representation, and here is the system's zero-state response. Only 3 terms can go through the system. And plug in these parameters, we get the system's zero-state response in the time domain. And here is the input signal in the time domain, and here is the output in the time domain. And we ignore the DC components in this graphic representation. Now let's summarize. The frequency analysis of the continuous time LTI system reveals the relationship between the input signal and the system in the frequency domain. And the frequency response H, J, omega reflects the frequency characteristic of the system. For a given periodic signal, the system's zero-state response can be represented as another Fourier series. For non-periodic signals, we can use the multiplication of the system's input and the frequency response. The zero-state response in the time domain can be calculated using inverse Fourier transform. There are some pros and cons for the Fourier analysis of the system in the frequency domain. It can show the change of the input in the frequency domain before and after going through the system intuitively. The cons include, first, it can solve the zero-state response only. We have nothing to do with the zero input response. The second is, if the system's frequency response or the input Fourier transform do not exist, then we cannot use the Fourier analysis to do the system analysis. So in the next chapters, we're going to try to introduce another tool. It's called Laplace transform to overcome these cons. Thank you.